Alright, well, the other day, I would have to say that I might have been...
I'm as mad as hell, and I'm not gonna take this anymore!
So, let's try this again. So, here we are. Now, someone said they like these when I used to do them back in the day. So let's talk about what's happened in the last little while. So, I've been thinking more about the wiring diagram and how important that is and everything, and maybe like potentially an idea of how to maybe derive it or something, or how to find something similar with all of the math to find out why, and maybe relate a few things while we're at it. So it's exactly what I did. It's been bugging me, but like, you know, 9 times 9 times 9 is 729. Now, 729. How is that familiar? I have a 712 on the whiteboard, so no go there. Probably fart around and get it somewhere, but I mean, one place I know there's a 729 is Ramanujan's number. 1729. Now, it is a taxicab number, meaning the sum of two different cubed numbers equals 1729, and it's the lowest number that does that, the lowest taxicab number, which makes it uber important probably. Now, the two different numbers that are cubed to come up to 1729 are the number 1 cubed and the number 12 cubed. And what do I keep seeing on this whiteboard everywhere? 112. The center cell is the value of 76. It is the 36th thing created, 112. The bottom left cell is the value of 1, but it's the 21st thing created. You're going to read it backwards, 112. The third thing, the 6th thing, and the 10th thing created have a value of 112. And that's where I see 19,290 magnets for the 5-cell energy solution. 3858 times 5 people. So a 9 by 9. The reckoner is a 9 by 9, so I wanted to see what a 9 by 9 by 9 Rubik's Cube sums to. It comes to 1729. So we got a cube of a block of number. Cool. What else is a cube that I own? Oh, the actual model of the cell. Alright. If it's a cube, we're not looking at the vertices, but we're more looking at the faces. Let's say that yeah, there's like the big ass wheel, but there's 3 of them, and then you have a positive x, negative x, positive y, positive z, negative z. So what do you got? Where's my thing? Well, this computer's horrible. So let's say every wheel is 36 different solenoids on one wheel. Like a ring of solenoids. And we got 3 per face, and we have 6 faces. So 36 times 6 times 3 equals 648. One away from 649. Jackpot. Buy your ticket today. What's the difference? 648 minus the 729 we got earlier from 9 times 9 times 9 for the reckoner is 81. There's a difference of 81, which is a 9 by 9. So my ears were a little perked there. Not only that, the missing 1,000 from the 729, and a difference in looking at something that I need to do, which is the wiring diagram, because you got one big spool of wire, and you go to solenoid whatever, 400 wraps, then you go to solenoid whatever, 400 wraps, until you're all done, all the wheels and all the devices, using that one spool. Okay? So probably should go through the, well, the reason that the faces have 3 wheels is because you try to look for balance. And I think that the size, and my guesstimations, is that you'll need 3 different wheels on a face to equate to 5 smaller wheels on a vertex. That's just, I don't think it's like a 2-to-1 ratio. That'd be too easy. So, that's one little thing I saw. And it got me thinking about other numbers. And other calculations I can do. And what the total solution might be, and yada 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 yada. Until I was looking more at language. That's why I have my phone. I can't need my phone here. So let's go to my internets. Who cares about the weather? See, I should have wrote this shit down when I was doing it. Okay, let's try to think here. How do I want to relate this? Oh yeah, I forgot totally. Let's move over here. Come on. Booyah. So, we're gonna go take a look here at, I don't know, this M right here. That 1,000 in Roman numerals is what it equates to. So, the reason I find this interesting is because I'm looking at the perimeter of the cell. Because this right here is a ring, not a 0. It's a ring, or sphere, or who the hell knows what. But all I'm saying is that if we take away the perimeter, because we're not using that ring, maybe we're not using that M. Because 1 plus 5 plus 10 plus 50 plus 100 plus 500 is 6, 6, 6. The extra 1,000 would make it 1,666. Okay. So I'm like, maybe that's where you get the other 1,000. Because 9 cubed plus 10 cubed is 1,729. So I'm starting to think, like, if I have a 666, which would be basically equating for the 6 of the center cell for 76. So now we have kind of like looked at that 6 as a 666 perhaps, and we need to find our 7s. I've looked at the 7s before, but the 1 7 I really want to take a look at right now for you guys. It's not the one. That's not the one. This is the one. Is the 7 in the 7 in the middle of the 174 magnets right here, and the one below it. So there's the 7. What are you left with? You're left with the blue 14. See it? And the 14 is just 2 7s. This will be important in a little bit. So I'll tell you about what I do next. So I'm looking at 174, but I want to look at it like, not that. I don't want to look at it like that. I want to look at it like this, but like this. Where the 7 would be in the foreground, and the 1 and the 4 will be in the background. So to me, that kind of makes our 777. And that's the one I'm going to choose. But if you look at the interior, not including the exterior of the 9x9, but just the interior 7x7. If this is the position 1, that would be the, if let's do this, purple. If this is position 1, and this is position 2, notice how it's a 6 and a 7. And then this would be position 3 of them summed, which is 13. And then you have the L. Then you have 110. And then you have the 174 and 174 to round it out. What I find interesting is that not the 1st, 2nd, 3rd, 4th, 5th, the 6th, and the 7th position are where you find your 174, 174, or 777, 777. So, I'm like, let's talk about the, here. Let's talk about the actual solution about solenoids. So, Ramanujan's number, 1729. This is where we first start talking about. Here. Damn it. I should stay here. 1729. Okay, so what happens with 1729 times 2 is equal to 3458. Now, 3458 is exactly 400 off of 3858, the number of magnets needed in the cellular energy device. Now, a long time ago, I said arbitrarily that just because of the sheer size and scale of the device and the gauge of wire going to be used, I wouldn't want to go probably past 400 windings. And here I am, find this number, we're looking for duality, and I'm 400 off. So I think this is a good sign. Everywhere there's signs. So there's 400 wraps per solenoid. There's 36 times 3 on the faces times 6. And on the vertices there's 36 with a smaller gauge of wire. 400 wraps times 5 times 8 because a cube has 8 vertices. So let's do the math. Nice angry people outside. So again, 36 times 3 wheels per face times 6 faces is 648. Now let's just write that over here. Words. I'll get to that later. 648. Now we have 36 times 5 wheels times 8 vertices is 1440. 1440. So if we add them together, you get 2088. I find this interesting because, I don't know, I got a cell with a 28 in it. A 28 in a cell. I don't know. So, that's the number of solenoids per one device. Total. If we multiply that by 5 devices, it comes to that. 10, 440. So if you look in the middle but you look backwards, it makes 440, like a frequency. Like the frequency they record music at. They don't like 432, they like the destructive properties of 440 hertz. Near around to 10. And throughout all these things I'm going to find later on, I'm always like a magnitude of 10 off, but it's like a 1-0 duality, whatever, all that stuff. But this right here could also mean you're trapped 100 and 44,000 trapped souls. Trapped. What does the solenoid do? Jesus Christ. Just to be clear, basically a solenoid is there to move electrical current to the starter. This makes it an absolutely crucial part of a working vehicle or any other project that requires power from a battery to a starter. Anyway, solenoid right hand rule. An electric current passes through a solenoid, resulting in a magnetic field. When you wrap your right hand around the solenoid with your fingers in the direction of the conventional current, your thumb points in the direction of the magnetic north pole. An electric current passes through a straight wire. Savvy? So, maybe I should, Alright, some of that. Is that okay? I don't want to do that. So, where are we now? Got a heckler outside. Gotta beat up the trash can soon. So, from a certain point of view, the number of solenoids needed in the entire 5-device energy solution has a similarity to the trapped 144,000 windings to trap current to make it work. I don't think they give you the number. They like to round. They like to take a 6-digit number, because 5 makes 6 and 7 is the nothing. It's probably like there's 5 actual characters working as one to become complete, and anywhere that touches the bubble to the inside number things will be the nothing, the 7th. Anyways, it's like a Yoda here. Well, maybe you look at the 4 faces of the tetrahedron, you get a Y, an O, a D, and an A. Because it's a tetrahedron. Yoda. Anyway. How old is he? About 800. Is he 729 years old? So, I started thinking, okay. This is where it comes in handy. So, when the entire solution, or this one, when the entire solution is done, okay, you're gonna have 14 axles, penetrating one device, 14 times 5, 70. Wait, that doesn't seem right. Why am I doing this? Because I'm tired. 14. Please be 70. Yeah, it is 70. Okay, good. So 70. 14 times 5. So, let me talk to you a bit about something. Okay, things happen for a reason. And up to now, nothing really important has happened with this. But I went to the washroom, and I come out of the washroom, and I usually do my best thinking with my dick in my hand. And when I come out, I go, what kind of shapes are there that have 70 nodes? So I Googled it. Let's Google it. 70 side, jeez. 70 node, Jesus. Kevin. Shape. Why is this in images? No, it doesn't like vertices. Yes. A regular heptacontagon. A heptacontagon. Obviously, it's a heptacontagon. So, well, let's take a look. Alright, good. Wikipedia, sure, let's do that. Imagine we had to open a book, guys. Imagine you didn't have the book. In geometry, a heptacontagon is a 70-sided polygon. The sum of any heptacontagon's interior angles is 12,240 degrees. Maybe that'll be interesting. Let's put it over here. Oh, we know it's degrees. So, a regular heptacontagon represented by whatever symbol can be also constructed as a truncated triacontapentagon, a T35, which is interesting, which alternates two types of edges. Okay, and then they give you this. This is where the regular heptacontagon properties really made me, really got me like pretty fucking happy about life. Really pretty fucking happy about life. The interior angle. One interior angle in a regular heptacontagon is 174 6/7 degrees. Meaning that the exterior angle, or every one exterior angle, would be 5 1/7 degree. Now, what's on the reckoner? Please. Oh, look, in the middle here. Oh, I gotta go here. Getting used to this. Apologies. We have a 0 with a slash through it, which a 0 could be a 1, a 5, and a 7. And I find it interesting we go from 5 1/7, which it kind of is. And the other one is 174 6/7, because it's not in the first, it's not in the second, it's not in the third, it's not in the fourth, it's not in the fifth, it's in the 6th and 7th positions of the reckoner. That's where it is. That's where it is. That's where it is. Now, up to now, maybe you didn't think I was onto something, because it's absolutely absurd what I'm doing. But when I found 174 degrees and 6/7 of a degree, sorry, and the center is a 76, you know, where's my thing? Where's my thing? Can I have my thing? There you go. 76. Remember I was talking about 7/7/7s? And I was thinking how it's 174 because you got a 7 in the middle. And then you have a 14 in the back, which is like 2 7s. You get 2 of them. Anyway. Let's just take that in for a second. shall we continue? So, let's go back to here. Now, that's the total number of the interior angle because it's 174 and 6/7 times 70, I guess. So, I thought about one more thing, and I said, I wonder if it works. Yeah, it does. Well, I can put it right here, actually. How many windings is that? So, yeah, we're good. Let's do 10440 times 400 windings per solenoid. I think it's 4 million. Yeah, it's 4,176,000 and a trio of zeros. So in the middle, pretty well. Maybe if the 4 and the 1 were circled, it'd be a 52, like the letters of our alphabet, the English alphabet, common tongue, or the language of mathematics. Now we have a 6 with a circle and a 0 left over. 76 is in the middle. Maybe it's circled of the reckoner. I don't know, guys. So I go, that's a lot of windings. Like, if you, literally, you need a big spool of wire. Well, you need two, really. You need two spools of wire because one's going to be 1 gauge for the faces and 1 gauge for the vertices, and they're going to have to each end go to something and something, and all of that. So, and they're going to have to touch the rings in the central heaven of each device, I guess. There'll be common points, but that's a lot of windings. I'm not thrilled to do that. No one in their right mind would be, which means that you probably have to build automated things to be able to, perfectly wind all your components, I'd say. Something like that. That's where my mind is going. So, now, that's the number of windings. Now let's divide that by 5 devices and see how many windings per device. It's almost 38, 50. Sideways would be an 8. And the 2 could be the 1, 1, which maybe unifies this with this. I don't know, guys, but anyway. So that's the number of windings per device. And let's say there's 14 axles. I know they're not perfectly balanced, like the vertices are going to have more than the faces, but let's see on average how many per axle. Ooh. It's about 60,000. 60,000 windings per axle is on average, but not really. So, oh no, wait, that was an actual important number, because look here, the answer. The answer, see that repeating pattern of 7, 14, 28, 5, 7, 14, 28, 5. See, it's right here. 5, 7, 14, 28. 7, 7, 7, 7, 7, 7, 7. 5, 7, 7, 7, 7, 7, 7, 7. And on and on and on for infinity. And all you have in the front is a 596. Or 569s, or I don't know. 569s and 596s and 569s, and then 7, 7, 7, 7, 7, 7, 7. Okay? What they're showing here, it says 5, 9, 6, 5, 6, 5, 7, 14, 28. And then it goes 7, 5, 7, 14, 28. 5, 7, 14, 28. So, 5 96s. Ugh, maybe that means like the this corner of the reckoner, the 8D infinite, and the 69s will be this corner. You know, let's we're allowed to assume. So the 569s backward, and the 569s forward. Then you have 7. Ugh. 2 7s. Ugh. And 4 7s. And it repeats. So, you know what I just did. Alright, so clear. Oh, that was horrible. So what am I talking about? The Ramanujan number. What is it again? What did I notice? 10440 divided by 1729. It's almost 6. It's really close to 6. And you got 38. And yeah, like a 1 and 7's like another 8. And then a 2 and 3 is like a 5. Anyway, it's not what I was doing. How did I get that? Oh yeah, because I remember now. I was looking at this going 38 and then 58 because it's 5 and 2 different ones. Jesus. 2 different ones. So I was thinking the 38 is on the left side of balance and on my left, and this would be on the right hand of my balance. So I was thinking maybe like the 38 and 58 something would be interesting because 5, 2, and a 1 is actually an 8. So I'm thinking this looks like an 8. There's your 5, and this would be a 1, 1 that could maybe put a bubble around the 5 and a bubble around these and merge maybe. So this is a very loose connection that Kevin had with the 38 and the 58. But what I decided to do was look at the 38th prime. This is right in my phone. No, yeah, so I somehow got the 58th prime number. I don't remember how I did this, but I asked myself, was 271 a prime number? And it said yes. And it said it was the 38th prime number. Yeah, it is the 58th prime number. So the 58th prime number is 271. So the 38th prime number I had to just Google, because I did some calculation to get the 271, I just don't remember what it was. When I found the 38th prime number, of course, it's 157, which is on our reckoner. One, 5, 7. And then we have this 271. Right here you have a 2, you have a 7, and you have a 1. This is what I did. I thought about it, and I remember that my 157 reminded me of the middle of the reckoner, and my 712 reminded me of, again, not looking at it like this, but not looking at it like this, but like this. and reading it backwards. So you'd have a 7's the middle, reading it backwards, 12. So I kind of got that from thinking like that about that number. Don't really remember how I got the 712, but moving on. So my heptacontagon blew my mind. Symmetry group is called a dihedral, d to the 70, order 2 times 70. Oh yeah, this is what I remember doing next. Okay, so next I was saying to myself, okay, I have these funny numbers. The 38th prime is very significant. The 58th prime is very significant. And I said, look at this, it's a 1, or it's 2, oh jeez, 2, 1 of 7 of 13, like a 1 of 1 of 7 of 13. It's 1 plus 5 plus 7 is 13. So I was thinking that's pretty interesting. Again, it makes me feel like I'm on the right track here. So what I decided to do next is look up a three-dimensional shape that had 70 nodes. So I'm going to look up I couldn't look up to Google, so all I knew what to Google was dodecahedron, because the interior of every model is going to have a dodecahedron with an icosahedron inside of it. A slightly smaller one that fits inside, because dodecahedron has 20 vertices and an icosahedron has 20 faces, which are all triangles. So I look up dodecahedron, and I'm like, okay, well, regular dodecahedron. I was like, okay, I don't know. So I clicked on this image button. I'm pretty sure it's gonna pop up again. Yeah, this one. And I see this page, and I go in my mind. I say in my mind. Let's click on it. That's not the right thing to click on. Let's click on it on the thing. And I'm looking at this, and I'm like, why? Just want to view image. View image. There it is. So I'm looking at this, going, that one's the most complex. And what I'm thinking is, whatever shape I'm looking for, solution I'm looking for, my solution is probably going to be the most complex. And I see that it's called, tell everyone, it's called a great stellated dodecahedron. A great stellated dodecahedron. So I go, alrighty, yeah. Great stellated dodecahedron. I don't even know what the hell this means. Jeez. So we click on this, and life's fun. So I think for this we should just go big internet. Does that work? So there's a little guy. Looks pretty. Kepler Poinsot polyhedron, so Kepler's involved. Regular dodecahedron, all the stuff on the side here. V's 12, faces 12, 20 vertices, edges 30. So this is 30 and 20 is 50. That would be 60. That would be 2. 62 and x is 2. I don't know what x means, but 64 elements. Faces, vertices, edges. Faces by sides, 12 and 5. Bunch of symbols and whatnot. So let's read what it says. I'm going to read the whole thing. Okay? Oh my god, the donate buttons. You want to donate to church or these guys, please. Please donate all your money to the church and Wikipedia. So, great stellated dodecahedron. Before we even start, this should be here. We're doing it. Because I know what great means. I don't really know what stellation means. All I know is that there's constellations, and there's 88 fixed rotating constellations in our sky. But maybe the con of stellation has something to do about what we're doing. So in geometry it says, stellation is the process of extending a polygon in 2 dimensions, polyhedron in 3 dimensions, or in general, a polytype in n dimensions to form a new figure. So I have a reckoner, which is in 2 dimensions. I have a model in the other room that I've derived, which is in 3 dimensions. And I believe that the planes that I have go from 0 to 8 dimensions. But typically, when united, I think they can go as far as n dimensions. So maybe what I'm doing with all of my work is a great stellation. I am doing a stellation. It's a process of extending in 2 dimensions, 3 dimensions, and n dimensions to form a new figure. Starting with an original figure, the Earth. The process extends specific elements such as its edges or face planes using a symmetrical way until they meet each other again to form the closed boundary of a new figure. The new figure is a stellation of the original. The word stellation comes from Latin, whatever, and in turn comes from Latin stella or star. Stella! Star. The stars in the earth sky. Kepler. Again, Kepler. I like Kepler. So, in geometry, the great stellated dodecahedron is a Kepler Poinsot polyhedron with whatever symbol 5 over 2. Mary kept saying it's like 5 over 2 pi, and then there's a 3 and 5s, and 5 and 3 is an 8, and it's 2, so 2 8s. So maybe this is a clever symbol for 3858. Anyways, it is one of our 4 non-convex regular polyhedria. It is one of 4. One of 4, guys. I've seen that before. 1 of 4. Oh yeah, I gotta do this. It's yeah, 1 of 4. 1 of 4. That's all I mean. It is composed of 12 intersecting pentagrammic faces. So pentagrams. With 3 pentagrams meeting at each vertex. Very interesting. 12 intersecting pentagrammic faces with 3 pentagrams meeting at each vertex. Wow, pentagram math, eh? It shares its vertex arrangement, although not its vertex figure or vertex configuration, with the dodecahedron, as well as being a stellation of a smaller dodecahedron. It is the only dodecahedral stellation with this property. Remember that. Oh yeah, I feel bad. Wait a second. Heptacontagon. The 70-sided circle with the interior angle of 174 degrees. Let's go back to this for a second. I forgot something important. Okay, because I got a little crazy when I saw the this. But if you go down, again, 70, it mentions is 2 times 5 times 7. No, 2 times 5 times 7. A 0 is a 1. Sorry. A 0 is a 1, is a 2 is a nothing. So this could be a nothing, a 1, or a 2. So again, I find it interesting that 70 is 2 times 5 times 7, which is nice. Since 70 is equal to 2 times 5 times 7, a regular heptacontagon is not constructible using a compass and straight edge. Now, what did the Masons like? Square and compass. A regular heptacontagon cannot be made using a square and compass. But it is constructible if the use of an angle trisector is allowed. A tool. So when I said it is the only dodecahedral stellation with this property, I find it interesting because the other one has another interesting property. My bad. Apart from the dodecahedron itself, its dual, the great icosahedron, is related in a similar fashion to the icosahedron. It is the only regular star polyhedron with a completely unique edge arrangement not shared by any other regular 3 polytype. I'll read like a retard. Shaving. Oh, I'm doing bad. Anyways, I just read its own thing, and you heard me. Shaving the triangular pyramids off results in an icosahedron. So if you take a great stellated dodecahedron and you shave off the triangular pyramids, you will have an icosahedron, which means there's a dodecahedron and an icosahedron here. If the pentagrammic faces are broken into triangles, it is topologically related to the triachus icosahedron with the same face connectivity but much taller isosceles triangle faces. If the triangles are instead made to invert themselves and excavate the central icosahedron, the result is a great dodecahedron. The great stellated dodecahedron can be constructed analogously to the pentagram, its two-dimensional analog, by attempting to stellate the n-dimensional pentagonal polytype, which has pentagonal polytype faces and simplex vertex figures until it can no longer be stellated. That is, it is its final stellation. What this means is that the icosahedron is inside of the great stellated dodecahedron. What did I say again? I said that the icosahedron is inside of the dodecahedron, like I've been saying for fucking years, which is why it's on the American flag portion of my whiteboard. I have the icosahedron is inside the dodecahedron, the octahedron is inside the icosahedron. All of this is inside of this cube, which is the thing we're building. But what I never knew is that fire, the tetrahedron, is not the result. It's actually being used to bridge the icosahedron to the dodecahedron. It said it in the text. Shaving the triangular pyramids off results in an icosahedron. Shaving the points off results in an icosahedron. Kind of looks like Canada. That's a big Canada in a big way. So, I have a name for it. That's cool now. So, what I do for a hobby is a stellation of a 9x9 reckoner that I've linked to Ramanujan's number and pi, and the tree of life and the flower of life and the seedlings of life, which are maple tree seeds that fall like helicopters. The great stellated dodecahedron, I believe, is the reckoner. Stellated. Let me repeat that. The reckoner is a stellated dodecahedron. Greatly. There's too many things that are too synchronistic to all this. An astrolabe is an ancient astronomical device that equates to a handheld model of the universe. Its various functions also make it an elaborate inclinometer and an analog calculation device capable of working out several kinds of problems in astronomy. Historically used by astronomers, it is able to measure the altitude above the horizon of a celestial body, day or night. It can be used to identify stars or planets, to determine local latitude given local time, and vice versa, to survey or to triangulate. It was used in classical antiquity, the Islamic Golden Age, the European Middle Ages, and the Age of Discovery for all these purposes. The astrolabe's importance came not only from the early developments in study of astronomy, but also effective for determining latitude on land or calm seas. Although it is less reliable on the heaving deck of a ship in rough seas, the mariner's astrolabe was developed to solve that problem. Now, a spherical astrolabe from the medieval Islamic astronomy is worth a Google. So the reason I'm talking about this is because Samuel de Champlain has an upside-down astrolabe at the place we call the astrolabe, Nepean Point. Well, the fireworks go off. Anyway, on Canada Day. On Great Stellated Dodecahedron Day. What did we just have? I can't wait till we have our 157th birthday in Canada. We're all going to lose our minds. I still can't believe 174 and 6/7 of a degree is a heptacontagon. The reason seven, so think about it. If you have 5 devices that are all doing 14 eddy currents each, they make 70 eddy currents. So imagine at the end of you need 6 devices. Remember I was kind of talking about you had the 6 devices, but the 6th device is just the fishbowl. So let's say you have one device here, 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 and one device here. I think this isn't a device. I think it is a fishbowl of water and stuff to dope the water. And I think what's going to happen is that actual eddy currents. Again, 5 will get you 6. 5 will get you 6. Meaning 1, 2, 3 will get you 4. The middle, which will get you 5, which will get you 6. Because a tetrahedron has 4 vertices. 1, 2, 3, 4, the middle dot, and the whole dot. And the 7th is the nothing. Remember, 3 makes 4, makes 5, makes 6. 1, 2, 3 makes 4, makes 5, makes 6. It's the Yoda principle. To create energy. The 6th is different. The 6th is different. Now, if the 6th is different, I thought to myself about 70 eddy currents. Imagine having like an eddy current. Not in magnetism. An eddy current is a circular current of water. The swirling motion of eddies in the ocean cause nutrients that are normally found in colder, deeper waters to come to the surface. You know? Eddy currents, people. Why do these suck? Here, that's a good one. I'm just not at the right everything right now. So I thought about 70 whirlpools being created. From all different directions to contain something. 70 eddy currents focused at a singularity somewhere in the room, where you go with your fishbowl of water until you start seeing your ping pong ball of solids, liquids, and gases being formed in your earth. Stick a wire, out a wire, to the input, get off the bike. That's the plan, Stan the Man, but, you know, I'm crazy for feeling so blue. Pretty cool, guys. Lot of synchronicities here. You might have to watch this a few times, but I don't know. I think I did well, or good. I don't know. Not bad. Cheers.